Okay. We will talk about how to design menu of contracts efficiently using randomization. So we study a classical principal agent problem. There is a game between a principal and an agent, and the agent chooses among personally costly actions. And each action defines a probability distribution over possible outcomes. And we have this second player, the principal, that receives a reward that depends on the outcome. The crucial part is that the action is hidden, so the principal only observes the outcome. And we focus on the principal goal, that is to design outcome-dependent payment scheme so as to incentivize the agent to play an action that is profitable for the principal. So this is an illustration of our setting. We have an arbitrary number of outcomes, omega 1 to omega m, and each outcome has a reward. Then we have an agent with an arbitrary number of actions. Each action has a cost and a probability distribution over the possible outcomes. While the second player, the principal, must set a vector of payments with a payment for each outcome. In this work, we consider a problem with types. So the agent has a type that is sampled from a known probability distribution mu. And the type of the agent determines the costs of the actions and the probability distributions associated with each action. So the game goes as follows. We have the principal that commits to a contract, P, that is made only by positive payments, so payments from the principal to the agent. Then an agent's type, theta, is drawn from a distribution mu that has finite support. The agent selects an action that maximizes the expected utility, that is the expected payment minus the cost. And the principal receives an utility that is given by the reward minus the payment. So our goal is to find efficient algorithms to maximize the principal's expected utility. And it is known by my previous work that this problem is NPR'd, and in particular, it is NPR to design a contract that provides a sublinear approximation in the number of types. So we extend this model considering introducing a type reporting step. So in this new model, the principal commits to a menu of randomized contracts, gamma theta, there are probability distributions over the contracts. Then the agent reports a type, theta hat, and the principal draws a contract P from the probability distribution gamma theta hat and communicates it to the agent. Then the agent plays a best response to this contract. And finally, the principal pays the agent P omega, where omega is the resulting outcome. We focus on menus of contracts that are dominant strategy incentive compatible. In this way, the agent is incentivized to report the true type. And so the principal optimal mechanism is a solution of the following problem, in which essentially we want to maximize over all the probability distributions over contracts, the expected utility, subject to the incentive compatibility constraints. Our first result is negative. We focus on deterministic menus of contracts, in which each probability distribution has support 1. Okay? And in this case, even if there are only 4 outcomes, for any constant alpha greater than 0, it is NPR to approximate the principal utility, the optimal principal utility, to within an alpha multiplicative factor. And moreover, there is no unadditive f-pitas for this problem, unless P is equal to NP. So without randomization, this problem is actually harder than computing an optimal standard contract, because we know from previous work that an optimal contract can be computed efficiently when there are a constant number of possible outcomes. We complement this result on deterministic contract, with some positive results. So we provide an additive pitas when the number of outcome is constant, and a polynomial time algorithm when the number of outcomes is 2, and a polynomial time algorithm with a constant number of types. So type reporting alone is not useful to design efficient algorithms. So we also need randomizations. And with randomization, we were able to design a polynomial time algorithm that computes an optimal dominant strategy incentive compatible menu of randomized contracts. So in the remaining of the presentation, I will try to give you an intuition of this result. And the first problem with the previous formulation, okay, of the optimal mechanism is that we have an infinite number of variables, because it's an optimization problem over probability distribution, okay, over R plus. So our first result is to bound the support of these probability distributions. We defined as P theta A the set of contracts such that the action A is incentive compatible for an agent of type theta, and this is a polytope. And then we show that there always exists an optimal menu of randomized contracts such that for each type theta, essentially the action A is induced by a single contract or none. And an idea of this result is that if we have 2 contracts that induce the same action, the same best response, we can replace them with a convex distribution, a convex combination of the 2 contracts. And in this way, since we are in a polytope, okay, the expected in which the utility are linear, the expected utility of the principal and the agent of type theta do not change. Well, the critical part is that the utility of another type at theta, choosing the randomized contract gamma theta, decreases. Then we have a second problem, that is that our payments can be arbitrarily large. Since we are working on probability distribution, it can be that there is a contract with an arbitrarily large payment that is played with an arbitrarily small probability. So with this second lemma, we show that actually there is an optimal solution in which the contracts are bounded. And to show this result, we lower bound the probability of each contract in this support of this probability distributions. And at this point, of course, if a payment is too large, then the expected payment is large, and so the expected utility of the principal is negative, reaching a contradiction. So using these 2 results, we were able to show that there is a finite set of payments that includes the optimal support. Okay, so we have shown that we can focus on PEC, so the set of bounded contracts, bounded payments. Then the last technicality that we need is that we define for each possible tuple of an action A, a tuple A of one action for each type. Okay, the polytope PA, that is the polytope of bounded contracts, such that this contract induces this vector of best responses, so A. If we define P star as the union over all the action profiles of the vertices of these polytopes, we can show that there exists an optimal menu of randomized contracts supported on this set. So now that we have a bounded support, we can write an LP, yeah. And so we can write an LP with exponentially many variables that are the contracts in the support, in P star, and polynomially many constraints. So as it is common in this setting, we can write the dual problem that has polynomially many variables and exponentially many constraints. These problems can be solved in polynomial time using the ellipsoid method, but to do that we need a polynomial time separation oracle. So an algorithm that, given a solution to the problem, find if there exists a violated constraint, and in this case it returns the violated constraint. So our last result is to show that this polynomial time separation oracle exists. And the idea is that we have an exponentially number of constraints, but we can split them in polynomially many sets, one for each theta and set of payment vectors P theta A. And here we are actually relaxing the problem because the union of these sets is a superset of the actual vector of payments, set of vectors of payments P star. And now for each of these polynomially many sets, we need to find the most violated constraint if it exists. And this amounts to solve a maximization problem. These maximization problems, okay, the variable is the payment vector, and these maximization problems are usually linear once we fix the best responses of the agents. And the idea is that since we restrict our attention to P theta A, the best responses of agent theta is fixed. So the first two components of these utility functions are linear, while the third component has a negative coefficient by construction, while essentially computing the best responses of the other agents is a max. Okay, we are computing the maximum over the set of actions. So this third component is actually concave because we have a minus and a maximum over linear functions. And so the global function is concave and we can optimize over it in polynomial time. So this allows to build a polynomial time separation oracle, and we can use it to solve our problem. Okay, brief recap. So we show that the computation of optimal contracts is an intractable problem in Bayesian settings. And we consider an extension of the model with type reporting and randomized contracts. In this setting, we show that computing menus of deterministic contracts is computationally harder than computing regular contracts. But we show that with randomization, optimal menus of contracts can be computed efficiently. And that's it. Thank you for your attention.
Okay, thank you very much. Questions?
Yeah, so nice talk. It's very interesting to see the randomization can help you overcome the complexity. I was wondering whether you can comment a little bit on the how practice is randomized contract. How practical? Like,
are you talking about how realistic it is to use these contracts in practice? Yeah. Okay. I agree that if we compare these randomized contracts with like linear contracts, I mean, there are settings in which linear contracts are implementable and usable, and settings in which these contracts are too complex. But I don't know, if we consider regular arbitrary contracts, I don't see any super complex difference between regular contracts and randomization over contracts. I mean, you only need something that allows you to sample from a distribution. I don't know, a rational agent that can handle arbitrary contracts maybe can handle also distribution over them.
Yeah, I would imagine it's hard to imagine that, let's say, get an offer from Google. Google was saying, okay, you know what, I'm going to draw a lottery and decide what's your salary. But anyway, we can talk about this.
No, you're right, you're right.
Thank you for the great talk. I have a question regarding the separation article you talked about at the end. So you solve an LP basically for the separation article, right? I was wondering if you've looked into, are there perhaps any special cases where this has a nice structure, some nice combinatorial interpretation, instead of just writing down an LP and solving it?
You mean you want an interpretation of why there exists a polynomial time separation oracle? Right.
Yeah, not so much the why. I mean, I can see the LP that you wrote. It's just that, I was wondering if for specific special cases there's some nice structure hidden there where you can express it in terms of like run a simpler algorithm than running the LP,
I don't know, I have no idea. I mean, the setting is complex, and I studied it in a general sense. So in this setting, optimal contracts are complex. And this is a weakness, of the model.
Yeah. But thanks.
One last question.
So in your setting, there are two types of private information. First is on the agent's types and also on the agent's actions. So is that correct?
Yeah.
Okay. So in your IC constraint, you basically have to ensure that agent, truthfully reporting type and also doing the best for the principal security in terms of actions, even after the agent first misreport on types. Right. So on the right-hand side of your IC constraint, you have to consider some deviations in terms of types and then do the best thing to maximize the principal security. Is that where the complexity comes from? You have to consider all kinds of best response on the right-hand side.
So if you look at the formulation, we only have the EC constraints or on the type you are reporting. Because the idea is that once you fix a contract, okay, there is a relation between the contract and the action that is optimal for this agent. So actually, for instance, in this problem, the best response is not an optimization variable, but it is simply a function of the payments. So we do not need to incentivize an agent to make an action, okay? But we know simply that if we will set this payment, then the agent will respond in this way. Okay, I think that the step of computing the optimal action is made a priori, and to determine that this action is incentive compatible and so on.
Okay, so in the interest of further time, let's take the other questions offline, and let's thank Matteo again. Thanks.